everybody. Welcome to my talk. I'll be talking about operating Pinot at scale. My name is David. I work on real-time analytics at Stripe. I work on the stream analytics team, and my teammates are in the front row. I'm here to talk to you today about some lessons that we've learned operating Pinot. So for the agenda, I'll go over how Pinot is used at Stripe. Then I'll talk through our cluster layout, how we automate operations through our control plane, some scaling limits we've hit, followed by how we iterate and improve on our SLCs. And finally, I'll conclude with some key takeaways. First, if you haven't heard of Stripe before, we offer a payments infrastructure that powers millions of companies around the world. We offer a wide range of fintech products and services to enable businesses to accept payments and grow their revenue. So some examples of this are products including Stripe Connect for running multi-party platforms, Stripe Issuing to create, manage, and distribute virtual or physical cards, and Stripe Atlas for starting a business online. Now, how exactly is Pinot used at Stripe? Stripe processes a large number of payments per day in real time for our users. We have various user-facing analytics products that give our users insight into how their business is doing. Pinot enables these products by enabling fast, accurate, and fresh data for merchants to make informed decisions about their business. And when a merchant logs into their Stripe dashboard today, they can actually see these real-time metrics on their dashboard, including things like total gross volume, how many successful payments they've made, and among many other charts. And many of these are actually powered by Pinot. So Pinot also powers some other products that we have, some things like billing analytics, developer analytics, seeing how healthy your Stripe integration is. And at our recent Stripe Sessions conference, we actually announced 2 features that our team was really excited about, usage-based billing analytics and fraud insights, which are also new Pinot use cases. Pinot also powers a variety of critical internal tools as well. So we use Pinot for financial data reporting, some administration tools to monitor risk, and payment method monitoring and alerting, and also security tools to monitor access logs. And if you caught this on Hacker News last Black Friday, Stripe published a microsite that displayed our overall transaction volume on our platform, along with many other metrics in real time. And a majority of these metrics were actually powered by Pinot. So now let's talk about how Stripe's journey with Pinot all started. In 2021, our financial data team piloted Pinot for an internal financial reporting tool over one of Stripe's largest data sets for search lookups and aggregations. The POC was overall a major success, and we took ownership of the cluster. This was a really large cluster at the time, and it actually had over 1,000 instances and over a petabyte of data. In 2022, the reporting data platform team piloted Pinot as well for a second POC to serve user-facing analytics. This platform powered various widgets and reports on the merchant dashboard. This POC also turned out to be a great success. In the same year, our team actually began to migrate a separate time series aggregation platform over to Pinot as well. And we had a series of reliability issues that impacted correctness of the data in the face of Kafka instability. So this largely motivated our migration over to Pinot because Pinot offers exactly once ingestion to mitigate these issues. And my teammate Johan actually spoke about this at RTA Summit in 2022. So we completed that migration of the time series aggregation platform in 2023, and the system has been running fairly stably ever since. This was a pretty large undertaking because we migrated well over 100 tables to Pinot and achieved better performance at lower costs. This year, we actually launched a beta Pinot platform internally that allows Stripe engineers to self-serve onto Pinot. Up until this point, many of our use cases users had to use frameworks that limited the flexibility they had to use the full feature set that Pinot offers. Users had to either fit these existing patterns that we already had or request and manage their own dedicated cluster. And now they can actually fully self-serve and create Pinot tables without our team's assistance. So this is a high-level overview of where Pinot sits at Stripe with respect to other systems. For data ingestion, Pinot consumes real-time data from our Kafka proxy, which handles consuming from multiple Kafka clusters. We have multiple Flink apps that sit upstream of Pinot, along with other publishers. And Pinot ingests offline segments from Spark pipelines set up by users. These pipelines often run downstream of Kafka archives or snapshots of databases. On the query side, we actually operate a Pinot query proxy, and some of them with very specific APIs. Teams call these proxies through their own services that they own. In terms of overall cluster setup, we primarily operate on EC2 infrastructure with local SSDs to optimize for performance. Our clusters are actually split by reliability tiers based on business criticality. So the highest tier being merchant-facing APIs, while our lowest tier maps to something like internal tools where it's less critical. We use separate servers for real-time and offline tables because the workload profiles are fairly different. Real-time tables often require more compute for ingestion, or they require more memory for upserts. And we configure our servers to use pool-based instance assignment for fast restarts, which I'll talk a bit more about later. And finally, we actually also operate our own internal fork of Pinot open source, and we try to stay relatively close to upstream. Now, by the numbers, in terms of our overall scale numbers today, we actually operate over 10 Pinot clusters with over 200 tables, using about 1,800 EC2 instances. We store over a petabyte of data in Pinot in aggregate, and we process about 1.5 billion queries per day and ingest about 80 billion events per day. So kind of our first operational lesson that I want to talk about is actually investing in automation early on. As I mentioned before, we actually, when we first inherited our first Pinot cluster, it was a very large one. The first cluster we took ownership of did have over 1,000 instances. We did not have any automation in place at the time, and many of our operations were very, very manual and relatively error-prone. This limited our ability to roll out configuration changes. And on top of this, Stripe actually has an internal requirement to replace hosts every 7 to 30 days for compliance. And since we had large tables on the cluster, server replacements even took hours to bootstrap from S3. Again, this is something we all did manually. So Stripe's existing automation for host replacements didn't quite work for us because it was not aware of Pinot's replica topology. And having it handle more than one instance at a time would actually cause downtime. As we spun up more clusters, we realized these issues were starting to compound and cause human toil and errors. And we were a relatively small team, so managing more clusters would simply not scale. So introducing the Pinot control plane. We actually built a control plane based on top of Temporal, which is a durable execution platform. This allows us to automatically ensure that this allows us to actually create restart workflows and replacement workflows for managing our clusters. If you haven't used Temporal before, it handles infra failures and automatically retrying and ensuring workflows continue to operate even when workers are deployed or replaced. And our restart workflow does batching logic that maximizes the number of servers it can restart. We use pool-based instance assignment, which allows us to programmatically filter servers by pools, since each pool maps to a replica group. And it takes at most, our restart workflow takes at most one replica group per tenant down in parallel. We also have segment and server health checks as part of the restart workflow, which checks after each batch is restarted to ensure the cluster stays healthy. And our instance replacement workflow uses the same underlying logic to replace hosts as well. This has been particularly helpful for instance type changes, like when we want to vertically upgrade to a new instance type. So this control plane has really allowed us to apply changes with a lot of confidence. More recently, we've actually expanded our control plane workflows to support user-facing workflows as well. These workflows allow users to self-service onto Pinot. So Stripe engineers can define tenant and table configuration in code, and they then call an API which triggers this workflow to apply the configuration to our clusters. This end-to-end workflow will provision EC2 infrastructure. It'll apply table and schema config changes. It'll rebalance tables for you. It'll also reload segments. And we try to serialize all our operations by tenant to ensure that multiple operations do not actually take down or impact any query availability. And one major design decision that we made was actually to do a restart of the servers instead of reloading segments. This helps with query availability because reloading segments can actually impact server resources. And by doing a restart, we're actually guaranteeing that the server won't process any incoming queries until it's fully up and loaded all segments. So we've received a pretty positive feedback about this workflow internally. And since users don't actually have to worry about the mechanics of operating a Pinot table. For our second lesson, be aware of limits with shared components. We've hit a lot of interesting scaling limits, I think, over the past few years that I wanted to share. So with some of our largest tables, one of the first few limits we ran into was with Zookeeper znode sizes. Our largest tables had grown to well over 100,000 segments. Pinot and Helix, Helix being the underlying cluster management framework that Pinot uses, store a mapping of segments to servers for each table in these nodes called external view and ideal state. If you haven't heard of Helix, if you click the Zookeeper browser in your Pinot UI, you can kind of see how some of this stuff is structured. Zookeeper has a hard 1 megabyte limit for znode size by default. And after hitting this limit, the writes to Zookeeper will fail. And ZK writes are necessary for many cluster operations like adding new segments, propagating broker routing changes, among other things. And writes failing would impair the cluster. So to fix this issue, we increased the limits on the Java system properties on Pinot and Zookeeper to allow writes to continue to work. There's an option called jute max buffer, and we actually pushed that to 10 megabytes and above. We also monitor max znode size as part of monitoring Zookeeper, and the metric here is called max proposal size. This gives us a rough idea of how large our largest znodes are. The recommended approach is to typically reduce segment count, which also decreases the znode size for those large znodes. But unfortunately, our segments are already pretty large in the gigabyte range, and backfilling them would be pretty prohibitively expensive for our largest tables. Another issue we ran into with Zookeeper and large tables is that rebalancing them would actually cause Zookeeper to run out of memory. This was caused by two separate issues. One, we had a lot of segments, so we had a large Zookeeper data set. Zookeeper stores its data set mostly in memory. And because Pinot actually stores segment metadata in Zookeeper as well, this segment metadata contains information like the S3 path and among other things. The other issue was that rebalances cause Helix to issue many state transitions to server nodes to make sure servers update their local segments, as segments need to move around as part of the rebalance. When we observed Zookeeper running out of memory, this caused a series of leader elections. Zookeeper was falling over. Overall, it was a pretty bad time. And we also saw reads and writes become unstable, which impacted other tables on the cluster. To mitigate these issues, we ended up scaling up heap on Zookeeper. And one big alert that we added was to actually ensure that the total heap size on Zookeeper was 3.5 times whatever the Zookeeper dataset size was. We've also enabled minimized data movement on our Pinot tables, which uses a different rebalancing algorithm than the default. This ensures that the segments don't shuffle significantly when new segments are added as part of the rebalance. And this allows less state transitions to happen on the cluster. We also found a setting in Helix to actually set gzip compression on all Zookeeper nodes. By default, Helix will do this at, I think, a 1 megabyte threshold. And we actually just turned it on by default for everything. This helped reduce the Zookeeper dataset size down by 40%, which actually shrunk a lot of our datasets a lot, which was great. Next, I'll get into some controller bottlenecks. So another limit we've run into with controllers, we've observed like a thundering herd effect when many real-time servers try to commit and upload segments to the same controller at the same time. This caused real-time tables using that controller to have ingestion lag. Restarting the controller fixed the issue, but we really didn't have a good explanation on why. And we also tried tuning segment flush thresholds, but didn't see much improvement. It turns out in Pinot, there is a lead controller for each table, determined by hashing the table name. And when segments are sealed, servers will upload their segments through the controller via HTTP calls. And those uploads actually use direct memory on the controllers. So it's possible to actually exhaust memory on the controllers or cause controllers to swap, which degrade the performance of the controllers, leading back to the ingestion lag issue that we had. To mitigate this issue, Pinot actually supports a feature called upload to deep store, where instead of using the controllers as the primary thing to upload segments to S3, you actually have the servers do it directly. So the segments still will commit through the controllers, but then they'll actually upload their segments directly to S3. And this actually helped alleviate the bottleneck, and we didn't see the issue again. And for the last lesson, I'd like to talk about tight feedback loops. So I think one good practice that we've had over the years is to actually use tight feedback loops to maintain our SLCs. Over the past 3 years, we've actually let me show you. Over the past 3 years, we've actually had target SLCs that have evolved over time. So here you can see our core SLCs. Our query availability targets range from 2 to 4 nines. Our freshness targets range from hours to seconds. And our latency requirements have ranged from 3 seconds to 75 milliseconds. So as you go left to right, our SLCs actually get a lot stricter. And if you remember at the beginning of the talk, I mentioned our journey with Pinot. The gradual strictness of the SLC is mapped with our journey of trying to achieve lower latency and availability with Pinot. Back to feedback loops. For our time series aggregation platform with stricter SLCs, it took a while to iterate and achieve the desired metrics. We were migrating from an existing platform that already had relatively strict SLCs, and we wanted to make sure that Pinot could maintain the same. We didn't have a lot of experience necessarily in getting Pinot to achieve the desired number, so that took a lot of iteration. What really helped was to create a tight feedback loop. As we migrated tables over from our existing system to Pinot, we routed dark read traffic to Pinot and actually measured the overall availability with respect to our existing system. So here you actually can see a chart of Pinot's availability metrics relative to the existing system, which is the blue line. And eventually, we were able to reach our targets. This loop really allowed us to experiment with different changes to see what worked and what didn't. And we reviewed it often whenever we rolled out something significant. Another feedback loop we have is a weekly metrics review. This helps us maintain our SLCs well after the system has been productionized. We review our SLC metrics weekly for misses or even near misses to identify issues before they become problematic. And we perform a root cause investigation and annotate them in our SLC charts so that, like you see in the example below. We try to understand if we receive the page or not. Is there a gap in alerting? Is there missing metrics? Is there some underlying infrastructure issue? And we try to get to that root cause. This practice has been really helpful in making sure we uphold our SLCs and often lead us to making significant fixes or configuration changes. So I'd actually like to switch gears now and talk about some fixes that we've applied as a result of these practices. On the freshness side, this is actually a feature that one of my teammates, Johan, helped contribute to improve our freshness metrics. But by default, Pinot actually waits 10 minutes when a server starts before marking as healthy and allowing incoming queries to be served. Because consuming segments, which are the ones that are actively being ingested from Kafka, are stored in memory, they are lost when real-time servers are restarted and servers need to re-ingest their data. So when they catch up on ingestion, they often can take time and significant compute resources. Using a fixed timeout isn't desired because you might come up too soon and you might start serving stale data. In order to mitigate this, we made the freshness status checker, which actually waits until the events are some minimum threshold of minimum freshness before the server is marked as healthy. And this checker will also set the server healthy if it reaches the max offset of the stream, so it can handle low volume topics as well. This was a pretty significant improvement. to our freshness SLCs and ensured that we were actually staying relatively close to them. Another improvement that we had added, that we contributed back to open source, was ingestion level aggregations. So this is a feature that my team worked on. But to reach the low latency needs of our time series aggregation platform, we use ingestion aggregations to only store the pre-computed aggregation value. So instead of storing like event level data in Pinot, we're actually just storing the pre-computed aggregation. This is kind of similar to the StarTree index, but it applies to the consuming segments as well. And this really helped push our latencies well below our 75 millisecond targets when we were having a hard time reaching them. So I would note here that this feature does limit schema flexibility a bit. Since you're no longer storing event level data, you actually will have to either generate a new table to actually get that data back or re-ingest to recompute those aggregations. And lastly, during one of our metrics reviews, we actually noticed occasional blips in availability. After investigation, we found out it was caused by servers transiently being unavailable for one of our high QPS clusters. We eventually landed on trying out adaptive routing, which is a feature that the folks at LinkedIn contributed. This feature makes brokers selectively pick which servers to route to based on the number of requests or the latency metrics of the servers. We carefully turned this on and monitored our clusters. And after we did, we actually noticed our error counts had leveled off significantly. And it eliminated some availability dips as well. So the chart below is actually a chart for absolute error count. As you can see on the left side, we had lots of blips in error count. And towards the right, after we turned it on, we started seeing it level off, which was great. So this feature has actually also been useful for rolling out new instance type changes because we get to see whether or not there are significant differences in latency based on what adaptive routing selects as which replica group to route queries to. So in conclusion, I just wanted to go over some key takeaways. In our experience, Pinot has been highly capable of meeting our high-scale requirements and strict SLCs. Reaching desired Pinot performance, from our experience, has been highly iterative. Like, we didn't get here. It took a lot of time to get here. It took a lot of work. And honestly, we leaned on a lot of features that the community already had, and in some cases had to build our own. Investing in automation was huge for making sure that we had leverage as a team, that we could both manage our clusters, operate more clusters, and also support more users. And other lessons learned wanted to share is be aware of any scaling bottlenecks in shared components. Hopefully the ones that I shared are helpful. And use tight feedback loops to maintain your SLCs. And I wanted to give a thanks to the Stream Analytics team at Stripe, my coworkers, Jackie and the StarTree team, who have been really helpful in getting us to this point, and the Pinot OSS community. And that's it.
All right, so I noticed you said EC2 instances. Did you explore using Kubernetes at all?
So internally at Stripe, we support stateless services on Kubernetes. Stateful sets is not yet supported, and that's something that we really need for Pinot. So that is definitely something we would like to consider, but it's also a pretty big effort to migrate at this point too. So yeah. Common pages. I think they vary quite a lot. I think more of our issues right now are related to new users onboarding that may not have necessarily provisioned the right amount of capacity, for example, for their tables. Like, I think a really common use case a new use cases that we've been seeing want to use upserts, and that needs a lot of sort of capacity planning to understand how much memory do you need, how many servers do you need. And I think aside from that, like, we've definitely iterated a lot on our detectors and making sure that we catch issues. Like, the standard stuff like checking for segment replica availability, segment availability is really key. I will say one thing that's been really useful for capacity overall is actually monitoring the QPS per core for brokers and servers to get a sense of if you need to actually scale out. So yeah, hopefully, does that answer your question?
Thank you for sharing this. So I have two questions. So first question is, for this stream analytic team, how big is the size to support this kind of Pinot usage, the team size?
Our team, I think, is 6, right? OK.
OK.
Yeah.
My second question is, like, for internal query to Pinot, how do you guys address that? Like, does those client directly talk to Pinot broker, or you guys have some proxy layer between the internal service and the Pinot cluster?
Overall, I would say we either have platform teams that have query layers that talk directly to brokers, so they kind of act as a proxy, or we actually own our own dedicated proxy right now. So users don't talk to brokers directly. We don't really want them to worry about which tenant they're talking to. We don't want them to worry about the underlying infra. We just want them to send their query over, and we figure out where to route it to. So we also try to do some isolation of traffic isolation in terms of priority. So this is a relatively new thing that we've been working on. But yeah, and nothing talks to brokers directly overall.
Hey, thanks for the presentation. A question about the SLCs, specifically the latency. I guess for Pinot has the broker metrics that tell you the latency, and there's percentiles on that as well. But for forming an SLO, and specifically measuring budgets and stuff like that, do you guys use that metric, or you guys have a separate way to measure that?
Yeah, we measure it at the query proxy layer or whatever is querying Pinot. A lot of that has to do with what are the requirements of that call. I think in Pinot's case, it's kind of hard to tell whether or not the query failed because of a user issue or our issue. But at that layer, we actually are well aware that, oh, Pinot didn't respond in time, things of that nature. So we try to focus our SLCs more on client-facing metrics, since it gives us a more end-to-end representative value.
Why did you choose a self-managed solution over a managed solution like what StarTree provides, for example? Yeah,
I actually don't have context on how that conversation started. I do know we've actually been working with StarTree since we've started using Pinot. I think, yeah, I probably have to talk to the team to figure out how that conversation happened. But I will say, StarTree has been a huge help in getting us to this point. A lot of the issues that we talked about, we've talked to Jackie about. So it's been critical in helping us get to this point.
Cool. You mentioned you guys use the pool-based instance assignment. I'm just wondering if that's the same as partitioning the segments. If so, or if not, then do you guys use any partitioning or sharding to segment the data?
Yeah, pool-based instance assignment is different from partitioning. I think partitioning is more of a table-level configuration. But we do partitioning for our data sets internally. So I think in a lot of cases, especially on the offline side, where we can run a batch job, partition the data, shove it to Pinot, we definitely do partitioning. It's really helpful for getting latencies down, particularly tail latencies down. So because you can reduce the number of servers you query, which has been helpful. So.
You mentioned towards the beginning of the presentation that you've been able to run Pinot at scale at a low cost, and I'm assuming that's cloud costs in AWS. So I'm just curious if you all have any kind of dashboarding or tracking so that you see how costs are ebbing and flowing over time. And I know you mentioned you're doing multi-tiered storage, but if there are any other things you've done to control the costs.
Yeah, as part of that whole metrics review meeting, we actually have a dashboard for costs. So Stripe internally, our efficiency team supports a dashboard that lets you see sort of breakdown by platform. We do monitor our costs. We don't use any sort of tiering solution yet, but we have explored some of that in the past. I think in the biggest case now, we try to do retentioning where possible. Pinot is definitely a lot more expensive than running something like Trino, where you don't actually have to store the data on servers, on disk. But yeah, like we haven't run into any major issues with that yet so far.
Thanks. Another one. So I think you, in one of the diagram, there's S3. Do you guys back up to S3? Because I'm wondering, because we're thinking of exploring the local SSD with backup to object store. But a challenge with that is, adding a new server, whatever. There's a lot of traffic to rehydrate or, bring the servers up to speed. So yeah. So I guess have you run into any challenges when you add a new server to the cluster?
I think I would just, let me think. For us, like the biggest problem we've had is with the largest clusters, where it takes a lot of time to download segments and load them into disk. I think I would say overall for like smaller use cases, that's definitely not a problem. S3 honestly makes servers effectively like easy to replace because they can always bootstrap from object store. So it has been useful in that regard.
So do you have any guidance on disaster recovery for Zookeeper failures?
That's a really good question. I do not. Unfortunately, it's been pretty painful when we have run into issues, things fall over. I will say the nice thing is that Pinot's data plane is somewhat decoupled. Like if Zookeeper goes down, you'll still be processing queries. You just might not be getting new data or things of that nature. So, but I guess the biggest piece of advice is over provision. Thanks everyone.